start the presentation. Yeah. So we left off with this figure last time, where we were looking at the gate valve. We're going to look a bit more at gate valves this time. But the first thing I'm going to show is a gate valve here, where I've tried to create sort of an animation just to show you where it's moving and everything. Yeah, thank you. See, we have a bit of a problem with these nail marks and everything, but we'll just try to make do without it. It's an electric screen, so I can't really pull it down by hand. So again, we have a gate valve here. So we have the hydraulic part on this side. You can see the spring has been drawn in here. So it's the fail-safe spring, the one that will close it if it loses the hydraulic pressure. And over here we have the gate itself. In the valve, and here is the production line going through here. So we need to move this opening over here so that we get the flow through it there in order to get it open. So what happens is that we start filling up this area with pressure. It's probably already filled with oil from beforehand. We start pumping in pressure on this side. And then as the pressure increases and becomes greater than the force of the spring, it will push the gate valve all the way over. So then we get the opening over here instead. And then as we sort of just maintain the pressure, we stop adding new pressure in here. We just maintain the pressure inside here. It will stay open. And then when something unexpected happens to the hydraulic force, we lose the pressure and it will snap all the way back again on the spring, so that it will close off the production flow, which is what we wanted to do. And this chart shows a bit of the forces that is needed on the actuator. So what we have here is that we have the stroke of the valve over here when it is pushing it open. So it's fully open over here and it's fully closed over here. And upwards we have the force needed in order to move the valve. So to begin with, we begin at point A. We get a pretty high force in order to start moving it, because now we are counteracting the springs and we are also getting a lot of force from the production flow. It is pushing at this flat surface, so we get a lot of friction here as well. So we need quite a lot of force in order to start getting it slightly open. So when we get to this point, there is a small crack opening. So then we have just a tiny, tiny opening between here where the production fluid can flow, which means that we get a lot less pressure on the surface here, so we get a lot less friction on it. So that's why we sort of get a drop in the force needed here, and then we continue pushing it. We are pushing against the spring now, and then we get it fully open. And this is where we keep it most of the time when we just want regular production. And then as it is closing, this will be more like the force needed by the spring in order to manage to close it, because it will be pushing. We have lost the hydraulic pressure that is compressing the spring. So now the spring is pushing it back. And as you can see, it gets easier and easier and easier for the spring in order to just push it all the way back. Which is sort of lucky, because it is when the spring is fully compressed, that is when it gives off its most amount of power. It will lose some of its force as it nears its full extension. So that's it's nice that we get where we need the most amount of force from the spring is right at the start, and that's when it's fully compressed. So that's when it's going to give us everything. And then as soon as we get to the point where the crack is more or less closing, it will just snap shut the rest, because then we are more or less done there on that one. So it's just a visualization of the forces needed in order to move these valves when you have when you're opening and closing off the production flow. So here are a couple of requirements for valves. So these are the kinds that we've been looking at, the 3-gate valves, where you have the hydraulic part up top here with the springs and everything inside, and then you have the closing part of the valve, closing and opening there. So the hydraulic actuator needs to be able to deliver at least 5 liters, usually up to 5 liters of hydraulic fluid inside here in order to be able to move the piston all the way. So we will need to fill this room with 5 liters of fluid. We have a distance requirement here. I'm not quite sure what they mean with this this part here. I think what they mean is 3 kilometers from the pump, the hydraulic source, and then it's 2 to 20 meters from this point and then all the way in there. So you can actually have the actuator placed quite a bit away from it. That's what I think this part means, but I'm not quite sure. There's no real description of it in the appendix, so it's not that easy to know. You have pressures of, well, they're given it in PSI. My recommendation is that anytime you see these imperial units, these PSIs and stuff, just open up your browser, go to the Google page, and just write in 3000 PSI to bar. And then in the autocomplete part of the Google search bar, it's going to automatically show you what it is in bars. So it's the quickest way of converting stuff. So if you have your phone ready or you're sitting by your computer, just do that. It's much easier than starting to look at conversion tables and putting it into your calculator. Of course, at the exam, you will not be given anything with imperial units. We stick to the SI units completely. So even though some places in the book they are referring to imperial units, I will, when I create the exam problems, I will make sure that you don't have to use any of the information that is given in imperial units. But in this case, it would be the liters or the distance, and it would not be the pressure if you were supposed to use this illustration in the problem. So I would avoid that for you. So we also have the surface controlled kind of valve, the surface controlled subsurface safety valve. And this is the one with where we have a flapper, which will flap closed if we don't have hydraulic pressure, so that it will swing up here and just close off the entire area, unless it has a certain amount of pressure coming in. And as you can see, this is a lot less, so the piston isn't really all that big in this one. So it's 0.1 to 0.5 liters, so that's not much, just a couple of deciliters. And we have a 4 kilometer reach for it, in order to be able to control it properly. So this means, of course, that the well can be situated 4 kilometers in length from the control site, which would be a platform or a floating vessel. But of course, it is 4 kilometers of umbilical line with the hydraulic hose inside it. So it's not 4 kilometers in a direct line; it's 4 kilometers along the. It be going in a curve, and it might be curved on the surface and everything. So the direct line will most likely be a lot less than 4 kilometers. So we also have the one we talked about a bit on Tuesday, the through flow line diverter, which comes right after the Christmas tree, basically, where the production flow is going through the straits. I think it's going either the production flow is going through one of the lines here, and then if we are going to send down a through flow line equipment and send it into the tree, it can't pass through the choke valve and everything, so it has to go through the loop and get up to the top of the tree and go through the valve on the top. So then we need to have a flapper valve here also, So I mentioned this just briefly when we were talking about it on Tuesday, that we need to have something that diverts this tool. So it diverts the flow into the opposite flow. There. Diverts the tool into the opposite of the regular flow. And then we have the, and here we don't really need much. It's sort of the same kind of valve as the subsurface control valve, subsurface safety valve. You just need a bit more hydraulic fluid in order for it to go, and you have a bit shorter reach on it. And then you have the choke valves. So we looked at those. There were a lot of different kinds. You had needle, and you had the rotating discs, and several different kinds of sleeves that you can use for those. But usually they don't require very much of hydraulic fluid in order to. So you can see most of the hydraulic fluid is more or less stable, keeps its position inside the hydraulic line all the way. So it's just moving slightly, just back and forth a bit as you are opening and closing these. So most of the fluid is more or less static. And this one also has about 3 kilometers of range. Yeah. Then we are going to talk a bit more about the sensors that we equip the Christmas tree with, because there's a lot of things we would like to know about the production flow. Basically, we want to know temperature, pressure, a lot of different things. So we have pressure sensors, usually both on the production line and on the annulus. This has to do with being able to equalize the pressure between those, to make sure that we don't get too much pressure in the annulus compared to the production, so that we can bleed out if the pressure rises too high. The temperature is usually only on the production side, just to know the temperature of the flow coming up from the reservoir. And this temperature can change from the tree and to the processing plant of the top side if you have quite a long flow line to go through, because it's going to be cooled a bit by the surrounding seawater as it moves through the flow line. So the temperature can change, but it is of course something that you can actually calculate. How much of a temperature difference will you have from start to finish during this flow line when you have around about 4 degrees Celsius of constant temperature surrounding it, because you would know the heat transfer through the steel pipe and its insulation and everything. So there's as long as you know the starting temperature, it's not really difficult to know what to expect when it comes up to the processing plant. And also for the temperature, they usually have pretty thick insulation on it. Concrete. It's a steel pipe, but maybe they have a thick layer of concrete around it and everything. So the temperature transfer doesn't really happen all that fast during the flow line. And it's of course nice to know if you have sand being produced through the flow. If there is sand that's coming up from the reservoir, and if you have any sand coming up, then it's really important to know how much you're getting, just to be able to sort of predict how much erosion are we going to get inside the flow line. So how often do we have to have service intervals to check the flow lines to see that they haven't been eroded too far. Valve position indications, which will be both for production and annulus, which is basically just, you can't be 100% sure when you are flipping the switch and telling the hydraulic system to open a valve or to close a valve. You can't be 100% sure that it's actually managed to do that. You can have a mechanical malfunction inside the valve, which means that it won't close properly or it won't open properly. And to the hydraulic system, it looks like it's done the proper thing because it's maintaining the proper pressure and everything. So everything looks fine, but it might be not all the way open or not all the way closed, so that you have a little crack or anything. So then it's very nice to have the position indication for the valve, so that you know exactly the position of the valve. So you get a verification of the of the closing or opening of a valve there. And also like the choke valve, you would like to know exactly how much are you now choking. And we talked a bit about leak detection earlier, so hydrocarbon leak detection. They have sensors for that also in production parts. This one was, need to find it here. I think this one has snuck into the wrong place, basically. Because it wasn't supposed to be that one there. Let's see if the next one is correct. Yeah, we're on guiding systems. That's a bit better. So we have two different kinds of guiding systems. This is the page 16 of the appendix, subchapter 5.6. So you have the ones with guidelines. So long as they're not too deep, then you have can use the guidelines all the way down. But then you also have the guideline-less. They are all that imaginative when they are creating names for things in the offshore industry. So the guidelineless basically means that you are just lowering the equipment down. You are not guiding it on wires all the way down. You are just lowering it down until it almost reaches its final destination on the seafloor, and that's when you start guiding it. So what they usually do with the guidelineless ones is that they have some sort of funnel which can sort of catch guiding tips or guideposts that are mounted on the either the guideposts are mounted on the base on the subsea floor, just like in the guide wire system when you have guidelines. Then you have the guideposts on the base itself, and the funnel will be on the module coming down. But you can also have the funnel on the base and then have a guidepost on the module that is coming down for the guidelines. It's just a matter of design, really, how you do it. So with the guidelines, as you can see with this one, it has let's see, the guideposts are hidden inside on this one. It's a bit of a usually, if you want a better view of it, the guideposts usually protrude out of the module so that you can actually reach the top and release the guidelines afterwards with the ROV. There might be some sort of release at the bottom here, which we can't see in this illustration. So it's an old system. And I know many of the old systems usually had all of the releases at the bottom because they were supposed to be released by divers because they didn't have ROVs. So that then they tried to put most of the stuff down by the bottom because then the divers could just work in that area. They didn't have to sort of climb the modules in order to manage to do stuff. That's not really a problem when you're more or less flying an aeroplane in a game. That's much of the feeling you get in an ROV simulator or in an ROV as an ROV pilot. It feels often like you're doing a plane simulator or something, because or a helicopter simulator, because you're sitting there with your joysticks and you have a lot of buttons to press and you're just watching screens. So it looks a lot like playing video games, basically. And I think at least that's what I've heard from the few people I know that are ROV pilots. The guys that have a lot of experience playing video games are actually the guys that finish with the top grades from the pilot schools. So it's a good practice to be playing games if you want that kind of job. So here we have an operation going on. They are lowering things down. They have guidelines on here. It's a bit difficult to see everything, so I've split it up. Just get to show it a bit better. So up top we have the ship. It has a working moon pool, it says there. Might be a bit difficult to read for you guys back there. It's 7 meters by 5.5 meters. So that's in the middle here. And you see this large structure on top of the moon pool. That's where they, first of all, they send the module into the structure. Then they lift the module up into this top structure. Then they can open the hatches there, so that they can open it to the sea. And then they start lowering it down. And inside here they have sort of a rail system that follows the module for a while into the sea. So the first 10, 15 meters maybe, these rails follow it down into the water before it's completely released, and then it's just going on the guide wires further down. So it's just to try to make it as stable as possible here in the top 10 to 15 meters where the waves have their most effect. Was there a question, or were you just stretching? And here it was we have a 70-ton crane here, and this one was, what was it, 40-ton, the crane that we have over here. We have a lot of space. We have 1,000 square meters of space on deck for placing modules and moving them around. You probably can see it here. It seems like almost they have rails like on a railroad. And that's because they are basically just driving the modules around on the rails in order to get them into the correct positions, and then they drive them into this structure where they lift them up. Then we get to the part where it's being lowered down. Here we can see some of the stuff we already know. We have a Christmas tree at the bottom. Here they've put a blowout preventer on top of the Christmas tree. They're going to do some wireline stuff here, so they're going to enter the well with wireline equipment to work in it. So what they have is actually a lubricator assembly up here. I don't really know the details around this, but what I'm guessing is that this tool that they're going to lower down, it needs some sort of lubrication on the sides in order for it not to snag completely. If it gets slightly narrower somewhere, and then it's supposed to just slide straight past instead of snagging on friction. So that's why it's being lubricated on the way down. Yeah. And up top we have the stuffing box on top. That I am absolutely oblivious as to what the stuffing box does, but I'm going to try to figure it out for our next lecture. It has something to do with the operation that they're doing here.
I have a question, sir.
Yeah.
Why would the vessel have 2 cranes of different capacity? Why not one that can carry maybe 100?
Actually, it actually has 3 cranes because it has. It looks like. This one doesn't have an ROV, but it has divers, so it actually has a crane to lower a diving bell there also. So it's just a matter of being able to lift all of the stuff that they're going to lift. So they often have extra cranes that, you see this one has 70 tons and this one has 40 tons. So that they have different capabilities. So it might well be here that by one of the cranes, but then other equipment can having to use the same crane. So it's just basically being able to get the flexibility of having several cranes, and also it's a bit of a backup because if someone has planned this and been very conservative, they made sure that the 40-ton crane will be able to lift everything that's supposed to be handled on this ship, which would mean then that they had in effect 2 cranes that they could rely on. So if one of them broke down while they were doing the operation, they could still do the operation. It would take a bit more time because they only had 1 crane to move stuff around with. They would have to unhook and rehook and do a lot of manual work with it and use a lot more time, but they would still be able to do it. They didn't have to go back to shore and fix the crane. So that's often one of the reasons why they have several cranes, just to have a redundancy, basically. Then we have an old animation of an Emenco guidepost system. Try to put it up on the screen here. There's the guide wire anchor from the Emenco company. You can see the locks going in there, and it's being lowered into the receptacle. This is one of those with where it's locked at the bottom. So one of the old kind where it was mostly done by divers, but it is still built in such a way that just a bit more back here. It is still built in such a way here that an ROV can still do it with its manipulator. You don't have to have a human hand in order to be able to move these parts. And I've also mentioned it a couple of times before that everything that the ROV is supposed to touch, it's colored orange. And that's from the NOSOC standard, which says that everything that's going to be manipulated by either a diver or an ROV is supposed to be colored orange, because the orange color is fairly easy to recognize underwater with poor lighting and cameras and stuff. You also, even if you have a black and white camera, it is easier to differentiate the orange color from the surrounding yellows and darker colors. So you can see a color difference then, even if it's black and white. So that's the whole point in just making it more visually easy to do the job when you're down there. Let's see. And here you can see one of the funnels used on the guideline list when they don't have a guidepost. So here you see the guides, so it's really quite a huge funnel that's being used. So here you would have some sort of post on the module coming down. It would hit the sides here, and then it would be led into the center, where it would have just a slightly less diameter than the center hole of the funnel, so that it would be locked into place there. Then we have the protective structures, yes. Here's more of a larger system. Here we have more of the structures around it. We've been looking at mostly the Christmas tree and the control modules and the stuff that is inside the center here. Now we'll be looking a bit more at the entire structure around it. So this is a structure which is there to protect this equipment. You can see that it has a protection roof that will come down on top of here to protect it from the top, so that an anchor won't drop right down on and hit the Christmas tree directly. And it also has all of these bars going on the outside in order to try to avoid anything snagging the Christmas tree itself and pulling on it. So it would snag the structure, but the structure is built to handle it if a ship snags it with an anchor or a trawl or anything. And here you can see the flow lines are coming in here. So the flow lines won't be directly protected, but they are often covered with rubble or sediment, so that they are often, if they are in areas where there's a lot of trawling for shrimps and bottom-dwelling fishes, then they are often covered by the sediment. So they go in with a quickness that they, after they have put the pipeline down on the seafloor, do pipes out in the streets here. We would dig a trench, then you would put the pipe down in the trench, and then you would cover it up afterwards in order to protect it. So we're going to look at the protective structures. So many of them are over-trawlable, so that if a trawl comes following a ship there, it will hit the structure and then it will sort of bounce across it, and then they can just continue trawling further on. That is often the case outside Norway, because the Norwegian government has decreed that as much of the fishing areas as possible are to be kept productive, so that they don't want the fishing areas to, if you have to create areas where they can trawl because they're going to break their trawls if they accidentally hit a subsea well, you will be basically creating huge areas of the ocean where the trawls won't go because they are afraid of their equipment being destroyed. So then you won't be able to produce any seafood from that area. So the Norwegian government at least tries to make as many of them as possible over-trawlable. But then you also have the ones that are trawl breakers, where it will basically catch a hold of the trawl and it will just keep it there until the ship breaks the line. Because the ship will just keep on pulling, and after a while the wires will just be broken for it. So here you see a figure of an over-trawlable structure. So the trawl will hit the side of the structure and it will just fall on top and go over it completely. So these are the hatches, the protected roofs that will be opened if we need access to something inside there. But usually they will be closed, so it will be completely flat on top of it. So there won't be any edges or anything where the trawl can be snagged. So it will just float straight across it. But then you have the trawl breakers, where they have deliberately built it so that it will actually catch the trawl, and it's going to, this line where going up to the vessel will sooner or later either break by the strain, or the ship will have to cut it, and the ship crew will have to just cut it up on the ship, because they figured out that, well, we're caught on this structure and we can't get off it, so we need to drop this equipment. We also have a chapter here about flow lines. So it's chapter 6. We're done with chapter 5. We have several types of flow lines. So we have the steel ones, which are the ones I've been talking the most about, which is just basically a steel pipe. Usually they come in lengths of 6 or 12 meters. There's actually a storage area pretty close to where I live, so whenever I do my jogging rounds, I jog past this area. They're pretty huge when you look at them. They're like this kind of diameter, and they're 12 meters long. Many of them already have a concrete covering on them, so that they're covered in concrete, about that thick of a layer of concrete, and then all the way at the ends there is about this far of a stretch where it's only steel, so the concrete doesn't go all the way, because they need to be able to get access to the steel in order to weld it, and then they put new concrete on top of the weld afterwards before they lower it into the sea. We'll look at more at when we get to the vessels. That's part 5, I think. So when we're looking at the vessels, we'll look at vessels that lay pipelines. So then you will get more of an understanding of how they actually do this welding and concrete parts on it. Then you also have these, a bit difficult to read there, so I'm going to get it up here. Then you also have the carrier pipes, where you have an external pipe, and then you have the flow lines inside. You have several flow lines inside one pipe, and then you have foam insulation between them. That's if you don't need really huge flow lines. If you need smaller flow lines, you can just gather them all. Instead of putting down many thin flow lines, you can just gather them all in one huge one to save some operation time out there. And then you have the flexible flow lines. So these are made more like a hose that you would see in a you're thinking like hydraulic equipment and stuff when you have a hose there. It is usually layered much like this. It has these sort of different layers of steel fibers that are going across each other in different directions, and this gives it a lot of strength, and it also gives it the possibility of moving a lot, because these fibers can move in relation to each other, but they will still keep it in their strength because they are crossing each other at different angles. So the strength is still there, but it is much more movable. And then you have a sort of top coating, plastic layer on the outside, keeping those in. And I think the inner tube is a thermoplastic usually. Keep it in because plastic is a lot more flexible than a pure steel pipe. But here you get the strength of the steel during these sort of meshes of thin fibers. So it looks if you strip away the outer plastic and you have pulled out the inner plastic, it looks kind of like a hollowed out steel wire. This kind of flexible flow line. So it's a very nice principle of getting a lot of strength. But of course, these are a lot more expensive than the other ones. So the flexible ones are used when you really need to be able to bend them. So for most part, you try to use the cheap ones if you can. So for the long stretches where you might have several hundred kilometers of pipeline just flowing in a straight line more or less, then you would go for the steel pipes. But as you are closing in on structures where you're going to hook it up, you might have to pull it at an angle in order to get it lined up for hooking it up to the structures. So then you want something that's more flexible, that will allow you more movement. And often the risers that go up to the platforms or the floating vessels, they are often also flexible, just to allow a greater weather window, so that they can handle much worse weather if they're flexible. Here you see a bit of a better image of it. So you see the steel parts going around here, and then they're layered the other way, and then you have someone that's more or less going the circumference on the inner layer there. They are just going around and around. Pretty much all these are going at a more or less 45-degree angle opposite each other. Here is from the Åsgard field. We're going to look more at the Åsgard field later on in this. So here you see. Yeah. Is it 10 already? Yeah. That will do a break. Okay, so I got a question about what exactly is a trawl. So a trawl is the fishing net that they use, and you have a fishing vessel up top with a winch at the back, and it sort of lowers it down, and then it has these weights out on the sides, and then it have these sort of sweeping wires that hold the trolling net in itself. And then as they pull this along the sea floor, they catch a lot of shrimp and all of the fishes that are living down on the sea floor. So they get quite a lot of fish in it, and then when they think they have a full net, they just pull it back up with the winches, and then they go to shore with it. Or actually, many of the fishing boats are actually large enough that they more or less have a mini processing factory inside the vessel, where they can just freeze them so that they can continue fishing until their storage holds are completely filled. So, but you can see the problem here, that if this structure is being pulled along the sea floor and it starts hitting stuff that are Christmas trees that are quite vulnerable to that sort of impacts, it won't be very good. So that's why they create these over-trollable structures, or create those that actually catch the nets and just make sure that don't troll here anymore. So, but usually the nautical sea charts where they can see where they are on the ocean. Usually they have sort of zones that are put in. So if there is one of these troll breaker structures placed somewhere, then there will be a zone of maybe a 500 meter radius around a half kilometer or a diameter of 1 kilometer then, of a circle that goes around the area where this troll breaker structure has been placed, just so that the fishing vessels know that we shouldn't troll straight across this one because then we're going to lose our nets. So then we have to make a roundabout way and go around it instead. But as I said, the Norwegian government tries to keep that to a minimum. They try to make the fishing industry and the oil and gas industry work side by side as much as possible. So, which is good because those are our two main exports, so it's needed. So here we have from the Åsgard field, we have this flow line, or it's one of these multiple ones. We have this one where we have several flow lines inside one huge steel pipe. So as you can see here, it's 42 inches across. That's pretty huge. You can see it lying here on land, waiting to be placed offshore as it's going along. And here we have gas injection. So that's going from a compressor, and it's going down to the wells, and it's going to be injected into the reservoir. Then you have two lines with production flow that's sending it back for processing. And then you have a couple of heaters here. So if I can remember correctly, that's a glycol solution. So that it's not just hot water that's being pumped through, because that would of course cause corrosion and stuff inside here. So it's glycol instead. So it's a sort of these antibacterial gels that you put on your hands. Those are mostly glycol with some alcohol in it often. And then you have the return there, which I am guessing is the heat fluid that they're sending down. It needs to have a return, so it needs to return back on that side. And this is just to keep the pipe at a certain temperature. So, because I can't quite remember if it was Åsgard or if it was Ormen Lange, but one of those two fields, they actually experienced that some places the surrounding water around the flow line actually went below zero. Because usually, when you get deep down into the ocean, it's usually around 4 degrees Celsius. But there, for some reason, it was actually below zero. But it's salt water, so it's not going to freeze or anything. So it needs to be even colder for it to freeze. But it was sort of a challenge because they had designed stuff to have a constant temperature of 4 degrees Celsius surrounding it. And then suddenly they had to take into account that it was actually quite a few degrees colder. I think they were down to -2 degrees Celsius. So that's a 6-degree temperature difference. That can mean a lot when you have quite a lot of kilometers of pipeline where it's going to go through. Then you suddenly have quite a long stretch where this temperature difference can have an effect. Here we actually have a small clip. This is also a 42-inch pipe. It was just more or less to get to show you. So I'm going to jump to 9 minutes approximately. So you see the dive on top, so you can really see the size of the pipe when it's 42 inches. That's the kind of pipes that they have stored quite close to the area where I live. So what they're doing here, they are lowering it down, so they're going to connect it to this part down here. And I'm going to fast forward to around 15. There you see the buoyancy elements, which they use in order to make it neutral in the water, so that it's a lot easier to move it. and you can see, you just barely see the diver there. So here you see the problem with sediments, because now he's moving around down there, and he's really swirling up the sediments, so that you get this sort of thick fog, so it gets quite difficult to see what's going on here. But he's doing a lot of stuff here. He's connecting, I think he's connecting some wires that they're going to pull it into the correct position with and stuff. So, but I thought it was nice to just show you how much this swirling of sediments can actually obscure your view when you're down there. So I really don't know how he sees anything at all when he's down there. So this clip is in here. So when the full clip is almost, I think it was 20 minutes or something. So you can, when we are done with Appendix A, I'm going to put this PowerPoint up on Fonto, so then you can watch the entire thing if you want to. So, yeah?
Considering the entire pattern, for the previous slide.
This one?
Yeah, the nitrogen.
Yeah.
Like, why did they use nitrogen?
I'm not quite sure if it's nitrogen as gas or if they have this foam here and then they filled the foam with the nitrogen gas. I think it's a foam foam insulation that they have in here. Of course, the sizes of these are probably much closer to each other. They're probably larger, so that they fill in the pipe much more than what is shown here. This is just me putting in circles just to show what's going where. Because I just had a picture of this one and it was all in Norwegian, so it was easier to just create a new one. But I think that it's a foam insulation that's between all of the flow lines inside there, and then they have filled it with nitrogen instead of having air inside, just in order to keep the oxygen away. Because then if something happens, if you spring a leak here or spring a leak there, I'm not quite sure which gas it is they're injecting. So if it's a flammable gas they're actually injecting, if there is a leak here somewhere and then you have air-filled foam here and you get a spark somehow inside there, maybe a trawl hits the pipeline or anything, and then suddenly you have a huge problem there because you actually have oxygen and you have something flammable and it's going to burn. And probably the foam insulation is quite flammable also, so it's going to create a huge problem. So I think they filled it just with nitrogen in order to if something happens, if there is a leak and then a spark, then there won't be any oxygen to feed the fire, so that there won't be any fire there, basically. Because you remember the fire triangle, where you need to have fuel, and you need to have air. What's the last one? You need to have heat. So if you have the fuel and you get the spark, but you don't have any air, you won't get any fire. So you will stay safe that way. So now we were over on. Let's see. This was the. Yeah, that was this one. These are two different ways of just connecting the flow lines. So the one over here you have a really poor illustration, but it's supposed to be diver assisted. So you have a diver down here that's connecting the flow lines, much like what we saw in the video clip now. And the other one is diverless, where you have probably an ROV somewhere in here. You can't really see it in the drawing, but the ROV is doing all of the work with pulling it in instead. So we will be looking a bit more at how they are connecting the flow lines later on. So when they are lowering down the let's see. Yeah, when they are pulling the flow line towards, because here you have the flow lines, going in towards the Christmas tree inside here. So when they are pulling these towards, they are doing it through what it says here in the text. They are doing it through sheaves. And sheaves are basically just discs, circular discs, where you have a groove cut on the outer part, where you can fit in a wire or a cable or anything. And the disc rotates. It has ball bearings in here. So the disc can rotate, and then you can have this being pulled across. So if you have a winch over here, and it will be pulling on this wire, and it can rotate across the sheave, and then it can go down instead. So it's just sort of a way of changing direction. Yeah?
Can you move backwards?
Yeah.
No?
Back one more.
Yeah. So what if the visibility gets very poor due to the segments?
Yeah.
What does it have to do with that? Does it just quit?
Basically, it just has to stop. So it just has to stop moving for a while, and then the sediments will sort of calm down again. Just like if you have a bowl of soup with a lot of let's say maybe it's a potato soup or something, where you have a lot of potato particles floating inside it. If you're swirling around with your spoon, it will become just completely fogged up with the particles. But then if you let it rest, most of the particles will just float down to the bottom, and then they will just lie there. And the top part will be fairly clear. So that's what's going to happen with the sediments also. So if it swirls up too much, then he just has to stop for a little while and just wait. But of course, it is better if he doesn't swirl it up, because he has his air in his tank there, and if he uses too much of his time, he's going to reach the limits of his air capacity, and then he has to go up in order to switch tanks, and then he has to come down again and continue work. That's going to take a lot more time than just doing it a bit more slowly moving more slowly while he's doing things. Because if he's not doing very sudden movements, then he won't be swirling that much water and sediments up. And that's also some of the things that ROV pilots use, that they try to keep their movements fairly slow and purposeful, so that they try to avoid sudden movements and stuff, so that they don't swirl the water too much. Which means also while they're moving around the area where they're working, they are not going full speed from one place to another to continue working there, because then they know that there's going to be a cloud of swirled up sediments that's going to follow them. So they try to sort of just glide pretty slowly over there. It's a bit more different for the diver, because he was basically standing with his feet in the sediment and working. So it's a lot more difficult to avoid swirling it up. So some swirling there will be, but he still has better vision through his mask than we do through the camera. So that he actually does, he sees better than we do through the camera there. So it's and he's the one that has to judge when he has to sort of slow down to let the sediments settle. Yeah, it was the sheet. How this one works? It's basically just in order to change the direction when you're pulling something from, you're pulling it horizontally and changing it to becoming vertical, for example, over the side of the ship, or through the tip of the crane maybe. By using this sheave, you could of course just have a rounded edge where you let the wire just flow across the edge, but that would mean that the wire would be dragged along the edge, and you would create a lot of friction. So you would do wear and tear through the friction on the wire, and you would also heat up the system. So the wire would be, when you were pulling it in, the wire would be heated by the friction, becoming warmer, and then it would be gathered into the drum. So you had in the winch itself, it will be pulling on this wire, and then we'll sort of just be gathering up the steel wire inside the drum then. And if the steel wire is being heated up by friction on its way in, then the heat is going to be trapped there, because it's coming layer upon layer upon layer of wire on top of here, and everything is heated up. So you're sort of creating a dangerous situation there, because these lifting wires are usually coated with grease also. so that and grease is flammable. So it's not a good situation to have very hot wires and coated with grease and everything. So using these sheaves, not only do you minimize wear and tear, because instead of being dragged along the surface, it gets to roll. So the wire itself stays into contact with the same area of the sheave along the entire rotation that it does around it. So as let's see. If we have this sheave here, we have a wire coming in here, and it's rotating. So this point of the wire as we rotate this one down here, this point of the wire up here will still be in contact with the same part of this disc that's rotating. So it's not being dragged across the steel of the disc, which means that we don't have this friction, we don't have the wear and tear, we don't have the heat being created. So this is something, especially if you're going to design lifting equipment and stuff, you will be in the world of sheaves when you're doing it, because they are an integral part of cranes and lifting equipment in general. Not the kind of lifting equipment that you are going to design in your project, because that's just a small part of the lifting equipment, but when you're looking at the big picture with entire cranes and winches, that's when you get these sheaves into play.
Excuse me.
Yeah.
So looking at the rim width, do you always have to change the sheave for every?
Yeah, because a steel wire will have a minimum bend radius. So depending on the thickness of the wire, it can only be bent to a certain radius, and that radius, or basically the diameter of the sheave, has to be larger than this minimum bend radius, or exactly the same. And also the rim width has to be because if you have a thicker wire, you need a thicker rim width up top there in order to make room for. So you really do need to have a sheave that fits the exact kind of wire that you're going to use. But of course the sheaves usually have sort of a range, so maybe you have from wires from 16 millimeters to 22 millimeters will fit in this sheave. But if you have a 23 millimeter wire, you should use the next size of sheave. And of course you have different bore diameters for what kind of axle size, shaft size you're using. So here's one where they're lowering down a module. So they're using sheaves up top here. They're also using sheaves up here. They're lowering it down, and here we can actually see they have these. It's a guideline list, so they have these funnel systems put in. And also, what they're doing here is that they are the ship here is actually laying the flow line. It's not helping lowering this one down. What they've done, instead of connecting the flow line down here, so that the ship would have come from the other end, come over here, placed the flow line down on the sea floor, and then they would have had to pull it in and connect it down there. So what they've done instead is to connect it up top here. So they've connected the flow line already, and the rig is lowering down the module, and at the same time the vessel is starting to lay the flow line. So as the module here gets down and is connected there, the flow line will hit the sea floor, and the vessel will start just moving it along to its final destination. So it will just start placing the flow line along the sea floor. So that's sort of a cheat on how to connect the modules to the flow lines, is to do it above the surface and then lower them down and do two operations as one, instead of doing a connection down below. But often this is impossible, because you have you might have flow lines that are already there that you're going to connect to. So it's sort of difficult. But this is an option if everything is ready for installing this module, and at the same time everything is ready for placing the pipeline. Then you can sort of do this, and it will save you time because you don't have to do 3 different operations. Because normally you would have to lower the module, put it in place, you would have to lay the pipeline, and then you would have to do a 3rd operation to connect everything. So, but here you do quite a lot of operations in one go. Did you have a question?
Yes, please. When you're lowering modules without guidelines, how do you compensate for waves?
We have the systems on the cranes, so they're called for heave compensation. So the heave motion is the up and down motion of the waves. But we are going to get very into detail on that when we get to the vessel part of the compendium later on, part 5. So we're going to look at a lot of the heave compensations and how these work. So here we have one way of connecting pipelines. This is more of, they show how to do connections if you have a leak somewhere in a pipeline, so that you can cut out a part of the pipeline and you can create bolted connections on each end of the pipeline, and then you can come down with a new one. So that's what this one shows. So yeah. So here we have a problem with a leak in the pipe. So they come down with a cutting tool and they cut off a section of the pipe there. And then at each end they place these connectors that will sort of clamp onto the end of the pipeline. And they're going to cut it open just to show us how it's done. These are hydraulic connections that I put on. So they are opening it up, and you can see here they have some balls. They are going all the way around, so it's much like a ball bearing. But the point is that they have these edges, so when they are pushing it, they are actually forcing the balls into the pipeline, so that it's sort of clamping shut. Then they lock it in place with that one. Connect with the hydraulics for here. So they have one connection going to the supply, and then they have just looped it around to all of them. And now what they're doing is that the hydraulic system is turning these huge bolts so that they are compressing everything here, which means that it is sort of pulling everything tight, and then you get a really tight seal here. There you can see all of the ball bearings. And then this one, I am guessing is because it's supposed to stay there for a while, so I think it's some sort of adhesive, a glue or some sort of concrete stuff that they are fitting in there to make it completely sealed. When they've done this on both sides, they can come down with a specially created piece of pipeline, and then they can just bolt it together with either a diver or an ROV. So then we're going to start looking at downhole equipment. So we've already talked about the different types of, or the different ways of doing work inside the well, which is, we've talked about the wireline service stuff, and we've also talked about the through flow line, where you pump it through the production flow line. So here is an illustration of the wire line. It's taken from on hand, I think. Looks like. We have a winch that is connected to the tool up top, and then you have all of these different valves and lubrications up top here. You send it down to the Christmas tree itself. The valves, the swab valve up top has been opened. Then you go through the entire thing and into the well itself. So then you can start doing work down here with the surface controlled subsurface safety valve. If you need to do something with that one, exchange it or maybe fix it somehow. I know they change them every now and then, the safety valves. So exactly how they do much of the stuff down here is quite difficult to sort of picture, because everything is done by remote far away and everything is just hanging from a wire. So it's sort of difficult to understand how can they actually be doing stuff down there. But I have a clip that I'm going to show you later on how it works. So that's how they get down on those. Yeah, I was actually already. This clip. There isn't much sound on these here because it's there aren't any good speakers connected to this one. So I'm going to try to do all the sounds myself. But if you watch them later on from the PowerPoint, you will get the links to YouTube and see the stuff. So here they are. Of course, this is on land, but they do the same on land. It's the same operation, only it's not. They don't have to lower it through water first to get to the Christmas tree. So it's just a short intro here for. Right. So here we have down in the well. Something as they're sort of showing different ways that it can get off center and stuff, so it can get stuck. Basically, so the drill can get. It was supposed to go straight down, but it ended up going in a curve, and it got stuck a bit. So what they are doing the wireline services for here is the fact that sometimes the drilling equipment just gets stuck down there, so you can't get it out. So what they are going to show later on is different ways of releasing it and clearing up the hole so that they can continue. Now it's stuck from here and down, and free up the rest. So first of all, they have to figure out exactly where is it stuck, because they need to know how much can they actually pull up without it being stuck also. So they go down with this tool, which does. I can't quite remember if it's electric readings it does, or if it was sonic readings, if it does ultrasounds, or if it was electric. But it will sort of give them a reading of where it's stuck and where it's not stuck. So as they lower it down, it tells them that it's not stuck, and then as they get further down, it suddenly tells them, "Whoa, here it's stuck." So it's sort of the same thing as if you have a glass of water, or a bottle of water. If you're sort of tapping it on the side, if it's half filled with water, you will get a different sound when you get down to the water. So it's sort of the same thing that they're doing here. So they're just checking inside the drilling line until they see where, okay, here it's stuck. They get all of these readings, and then they have to calculate. I'm pretty sure the equipment doesn't look like this anymore. This is a fairly old clip. And here's some of the equipment that they're going to send down. They're going to lower it down in order to start. Yeah, they're still checking checking where it's stuck. So it's pretty fanciful looking equipment that they're using. Putting it down, so it's quite. They've really used their imaginations when they've created this kind of equipment to detect stuff deep down inside the well. So what they did now was that they did a controlled explosion inside there, a small controlled explosion. And what it did was it shook up the pipe enough so that they could unscrew it above the point where it was stuck. They can also go down with acid, and they can just cut directly in the pipe. There you see the edges of the pipe after they cut it. Can't quite remember. And here they're also cutting with a jet instead, so they have different ways of cutting it. But as you can see, when they're cutting with the jet, they are deforming it. With the acid, they just burn the hole basically. But with the jet, they are really deforming the steel. So they make a fairly controlled explosion, which is strong enough to actually just rip apart the pipe. Here they're just illustrating that you can use the exact same techniques on a subsea well as you do on a land-based well. There you see one of the, this is a winch with a huge drum. Can't quite remember what it was that they were doing on this point. Yeah, that was the last one was that they were breaking it apart into several pieces just to get it unstuck. So they filled it with something that broke it apart. And now they blasted all of those pieces into even smaller pieces with a controlled explosion again, that they just sort of pulverized everything. Because usually the drill bits, they're not made to drill through steel, they're made to drill through stone and rock, just all the way down. So if you have something of the drill that is stuck down there, you really have to completely destroy it if you're going to be able to drill through it later on. There's one more here, but I think I'm going to save this one. It's a bit about fracking and how fracking works. I'm just going to show a small part of it, but we really need to have sound on, because the explanation is sort of the whole point with this one. It's not just showing stuff, it's the guy that's explaining also that's important. So I'm going to save that one. We are almost done for today, so I'm saving it for Tuesday. So we're going to watch it then. But then we'll be down in F again, so we'll have the speakers on there. This one was the just to show a bit on the through flow line way of doing stuff. I think I'll actually go with this one first. You have the platform itself up here, and you have the flow line going down and to the well, and then into the Christmas tree, and then into the well itself. So what happens is that they pump this a string of tools basically. So they string them together. So they have to make them because they have these bends on the flow line. They can't make the tools too long, so they have to make them to a specific length, and then they have to string them together instead, so that they can make it through all of the bends of the flow line. And then they will make the tool flow all the way down here. And what happens is when we get to the Christmas tree, we get this schematic here. So we have the flow lines coming from here, so they're going over here. We enter this one. Here is the diverter, the flapper valve that we looked at. So let's go into this loop and all the way around, and then into the tree itself. So it sort of just does a roller coaster loop basically, and then goes into the well. And then it's a matter of adjusting the pressure inside the flow line in order to get to stop at the correct spot, because you have pressure coming up from the reservoir, and then when you are counteracting that, you are pumping up more or less the same pressure, but then you are pumping it to a certain point so that it will be pushed down here. But then when it gets to roughly the correct location, the pressure from the reservoir will sort of equalize with the pressure from the other side of the tool, so that it will just stop there. So it will just stay there. And then they can, through a umbilical wire that's going all the way back to the surface facility, they can do tell it what to do basically. So it's much the same as what they do with the wireline stuff, where they can do controlled explosions if they want to. I think at least they can with these. They can do sort of different stuff with these through flow line tools. Do them remotely. Then when they're done, they just stop the compressor from creating pressure through here, and then it will be pushed back by the pressure of the reservoir. So then it goes back to the platform. Of course, they don't just stop the compressor. They have to slowly back down on the pressure, just so that it doesn't come like a bullet flying through the flow line and straight up to the platform. I think we'll stop there for today. We'll continue on Tuesday.